In this lesson, we are going to continue with financial applications. Actually, we're going to conclude what we're going to do with them. Last lesson, we looked at future value of an annuity. The logical next and final step is present value of an annuity. So remember, an annuity is a series of payments at regular intervals, right? So we make a same payment, same regular intervals, and the term is the time from the beginning of the first payment until the end of the final payment interval. The present value is the value at the beginning of the term. So again, future value told us how much your investment might be worth at the end of the term. Present value is the value at the beginning of the term. It's the sum of all the present values of the payments. So just as we used a number line in the last lesson to see where the formula came from, we can think about it the same way for this lesson. So if these are my payments, it could be years, months, weeks, whatever. Those are my regular payment intervals. So my time 0 is here and here, and then maybe 1 year later or 2 years later, whatever the time intervals are. R just stands for my regular payments. So we don't have a dollar value in here in this example. We're just, R could be $100, it could be $1 million, it could be $5, whatever, but it has to be a regular amount. So whatever that regular amount is, we're working backwards, right? So if I want to have R dollars, let's say it's years, just to make it so I can talk about specific time. It doesn't have to be years, as I pointed out, though. But let's say I want to have R dollars 1 year from now. Well, then I don't need to invest R dollars now. I need to invest R dollars times 1 plus I to the negative 1, right? So it's that formula. And again, it's easier with specific dollar amounts. Let's pretend that R is $100. Well, I don't need to put $100 in now. I need to put in a little bit less so that it'll grow to $100 in 1 year. So that would give me 100 times 1 plus I. I, again, depends on what the interest rate is. But that negative 1 is the key, because that's going to give me an amount less than what I started with. That's going to cause my calculation to become less than what I started with, $100 or whatever. And then, say I wanted to have, another $100 or R dollars or whatever 2 years from now. Well, that's going to have more time to grow, isn't it? So the formula is going to be basically the same, except instead of having a negative 1 as my exponent, I'll have negative 2. And we can see how that's going to carry on payment by payment, time period by time period, until we get up to whatever n is, whatever the last one is. Could be 10 years, could be 50 years, it could be 30 weeks, whatever it is. N is our last one. So this would be our third from last one, n minus 2. This would be our second from last one. N is our actual last one. So we carry on, and so for this one, it would be R times 1 plus I to the negative n minus 2, and this one would be R times 1 plus I to the negative n minus 1. And this last one would be R times 1 plus I to the negative n. So there's a lot of things that are the same. Each of these payments is a little bit less, I guess. I should point this out actually first. The biggest amount I would have to put in would be this one, because it's got the least amount of time to grow to be R dollars here. The least amount of money I would need to put in would be this one here, because it would have the most amount of time to grow to be R dollars there. So what's the same in each of them? Well, obviously they all have the same amount, whatever R is. So that's my common payment, right? The common ratio that it's growing by, it's a geometric series, and it has a common ratio of 1 plus I to the negative 1. So each time I go from one payment to the next, then I can multiply by 1 plus I to the negative 1 to get the next one. So that's my common ratio. and we have a total of n terms. So if you go back and think about our geometric series formula, you might have to refresh your memory, but this was our formula for geometric series here. A was supposed to be my first term in the geometric series. So this is my first term here. It's r times 1 plus I to the negative 1. And my common ratio, as I pointed out, is how much we multiply by each time in order to get the next term. Well, that's 1 plus I to the negative 1. And n, of course, equals n. If I plug these values in, let's highlight them in different colors so I can show where I'm plugging them in. So if I plug in 1 plus I, r times 1 plus I to the negative 1 in for A, then it goes in there. And if I plug in r here and here, because r shows up in this formula in two different places, that goes there. And n is my exponent, of course. And so that's just going to stay as n. Then if I simplify it, we can, here's some math that walks us through it. So 1 plus I to the negative 1 minus 1, remember this negative 1 exponent here just means that we can write this as a fraction. So we can write it as 1 over 1 plus I to the positive 1. And then if I want to simplify further in the next step down here, subtracting this 1, I need to have a common denominator in order to subtract. So I'm just changing this minus 1 to minus 1 plus I over 1. And there's a bit of a typo here, it looks like. This should not be 1 plus 1. It should be 1 plus I. Because if this, anything over itself is going to just equal 1, so that's going to equal the 1 here. So I've got a common denominator if I do that. And then I can just subtract the numerators. 1 minus 1 plus I becomes 1 minus 1, and then the sign changes in front of the I, giving me negative 1. Simplifying 1 minus 1, those terms cancel out here, leaving me with just the negative I over 1 plus I. And then I can rewrite it as a power, so I can, instead, these two things are equivalent again. I can just take this denominator, 1 plus I, as a denominator and write it as 1 plus I to the negative 1 to put it all in one line again. And so then I can substitute that back in to the formula for S sub n. And now I've got in the denominator of this formula, I've substituted this in for this, into this place now, right? And when I do that, then I can divide the top and bottom by 1 plus I to the negative 1. So in other words, these two guys here cancel out, these terms that are in both parts. So that's where they go. What am I left with on the bottom? Well, I'm left with negative I on the bottom only. And then still the r times 1 plus I to the negative n minus 1 on the top. And just to get rid of that negative I on the bottom, we can multiply the top and bottom by negative 1, as you can see we're doing here. So that's going to change this negative I to a positive I on the bottom. And as far as the negative 1 on the top goes, we could put it out front, but it ends up just sort of getting stuck. This negative sign, we stick it in here, as you can see. We're going to multiply both the terms inside the brackets by negative 1. So that gives me the negative here. That turns this to a positive. And then finally, just to clear away a few of these things, finally, all we do is swap places between these two terms so that the positive 1 comes first. So it's just tidying up. it's sort of long and involved, this explanation I just did, but it's really just tidying up this formula. The long story, to make a long story short, is that this is the formula for present value of an annuity. And this is all we have to use now in order to solve problems. So we can take present value and use it for different formulas that, or different word problems that we need to solve. So again, we need to know that R is our regular payment, I is the interest rate per compounding period, and N is the number of compounding periods in this formula up here. So let's put it to use. How much would you invest now at 8.3% per annum? So that /A again means per year, compounded monthly. So we know from previous experience that that's telling us that that we're going to do it 12 times per year to allow for $500 per month withdrawal for the next 10 years. So just like we've been doing, we should write out all the different variables that we're working with. So R is our regular withdrawal. So that's going to be the $500. And I is going to be 0.083 per year, but divided by 12 because it's monthly. 0.083 divided by 12 gives me 0.006916 repeating. 0.006916 repeating. Let's make sure I got that right. I think I did. And N is going to be 10 years times 12 months per year, so 120 payments. So how much do you need to invest now so that 10 years from now that you can take out $500 per month for the next 10 years? Well, let's just crunch the numbers. PV, present value, is equal to 500 times 1 minus 1 plus I, so 1.006916 repeating, to the exponent negative 120 all over let's see, 0.006916 repeating. Okay, let's put that all in the calculator. 500 times 1 minus 1.006916. Let's do a bunch of sixes there. To the exponent negative 120. Divided by 0.00691, and then a bunch of sixes. And for that, I got $40,677.37. So, does this make sense? Well, we can always check it. We want to take out $500 a month for 10 years. So how much is that we're taking out? $500 a month. 500 times 120, N, equals $60,000. So, the way I'd interpret this is that if I invest $40,677.37 now at 8.3% interest, it's going to earn some interest over the next 10 years. And it's going to earn enough interest so that I can take out exactly $500 a month for 10 years, and I'll have nothing left at the end, but I won't have gone over either. So how much interest will have been earned? Well, it's the difference between the $60,000 I'm withdrawing. I'm taking out $60,000, but I only put in $40,000, and so the interest is going to be almost $20,000. I'll use capital I for interest, so it's going to be 60,000 minus 40,677.37. I think it's 0.33, isn't it? Did I say 37? Yeah, I'll change that to a 33. So I just noticed a little mistake I made there. Change that to a 3. And the answer is 19,322 and 67 cents. So that's one use for the application of present value of an annuity. Here's another one. If we have we can use it to calculate loan payments. So Mike wants to buy a $40,000 vehicle on credit and make monthly payments over the next 5 years. If the dealer is offering 2.9% financing, compounded monthly again, what will Mike's monthly payments be? So again, this time we're trying to find out what R is. So the final amount, well, the present value actually is $40,000. That's how much the vehicle is selling for. I is equal to 0.029 divided by 12, again because it's compounded monthly. .002. We get these long decimals, especially when I'm doing on the iPad where I have to keep flipping back and forth. So not quite as convenient as if I had a separate calculator, but I want you guys to see what I'm doing. So anyway, 4.16 repeating after that. That's my I value. N is 5 years times 12, so 60 payments he's going to have to make. But this time we're finding R, so maybe it would be worth our while to rewrite this formula in terms of R. Maybe I'll do it up here so that you have it, so that we have it. Well, no, I'll do it down below. All right, so let's just do it over here. So if I start out with PV equals R times 1 minus 1 plus I to the negative N all over I. Rearranging to get R by itself, I'm going to have PV times I, and then I can divide the whole thing by 1 minus 1 plus I to the negative N. So that's my formula if I want to isolate R. So I haven't left myself much space to do it, but luckily being on an iPad, I can give myself extra space. Here it is. So in this case, R is going to equal 40,000, that's my present value, times 0.002416 repeating, all over 1 minus 1.002416 repeating to the negative 60. That's my N value. So 40,000 times, I still have the interest from below or from above, and then divide that, and I'm going to put this in brackets, 1 minus 1, actually I'm going to do it this way, 1 in brackets, 1 plus, and I'll just again grab that interest rate answer from before, to the exponent, negative 60. I get 716.97. So that would be the regular payment. So if you want to buy a $40,000 vehicle, finance $40,000 over 5 years, and you're paying interest, right? You're paying them 2.9% interest for the because you're going to get the vehicle now, but you're not paying for it up front, so you're going to have to pay interest. It's going to cost you $716.97 per month. That's going to come to more than $40,000, right? Because when we borrow money, obviously we have to pay extra. How much more? Well, it's going to be this $716.97 times the 60 payments will be the total amount paid. So take this previous answer, multiply it by 60 payments, and I get $43,018. And 29 cents. How much of that is the extra, is the interest paid? Well, it's the difference between the price of the vehicle and the amount paid, so that's going to be the $3,118.29. So there you have it. Present value. We can use this formula to calculate regular payments. We can use it to calculate how much money we need to invest now so that we can make regular withdrawals. But the key idea in this one is we have the money up front, and we're either making or getting the payments afterward. And so it's sort of working backwards compared to what we did for the future value. Give these questions a try and see how you do.